Good morning, everyone, and welcome to my presentation. Let me start by saying a few words about me. I am Manishira from Computer Science Department, 5th SEM. As we can see about your screen, our topic is today asymptotic notation. We have discussed about asymptotic notation. The main idea of asymptotic notation analysis is analyze the worst, average, and best case of an algorithm. Measures to efficiency an algorithm that don't depend on a machine specific constants and don't require two algorithms to be implemented and time taken by a program to compare. We know that asymptotic notation is a mathematical tool. It's like to represent the analyzing complexity, space, or time using this. Our next slide show the asymptotic notation. Asymptotic notation are a programming language that allow you to analyze an algorithm's running time by identifying a behavior and input size growth. This is also referred to as the algorithm growth rate, but it is not compare any algorithm head to head. It's compare that space and time complexity. It's compared to algorithm based on their change, their performance, input size increase, etc. We know about this asymptotic notation. And then next slide. Types of asymptotic notation. There are mainly three types of notation here: big O notation, omega notation, and theta notation. And the two more asymptotic notation used to represent time complexity of algorithm. It is not so used, but it's here: little omega, little o asymptotic notation, and little omega asymptotic notation. Big O notation. Big O notation represents the upper bound of running time algorithm. There is a gives a worst case complexity. It is specify the upper bound of a function. The maximum time required by the algorithm for worst case time complexity is return the highest possible output big O for given input. It is most widely used notation. Not so used, but sometime it will be used. Big O, big O notation basically represent worst cases. We see that here. Next we see that this graph there ha there have two function f of n or g of n, and c is a constant. If we describe the running of algorithm, we see that mathematical representation f of n is lesser equal to cg of n. That's why it's a upper bound. This is upper bound. That's why we see this graph. It's reason the highest possible output value big O given input. The execution time serves as an upper bound on an algorithm's time complexity. Omega notation. Omega notation represents the lower bound of an running time of an algorithm. Thus, it provides best case complexity of an algorithm. The execution time serves as a lowest bound on the algorithm's time complexity. It is defined as the condition that allows an algorithm to complete a statement execution in shortest amount of time. Yes, we can see this graph, then we are clear this phenomenon. We hear that we see that f of n a function and g of n is a function and c is a constant. The intersect point is n. Let's see this mathematical representation, this omega. If f of n lesser than c of gn, you can see that. Let g and f is a function from the set of natural numbers to the itself. The function f is said to be omega of g. If there are constants c greater or equal to 0 and natural number of no is a intersecting point such that c of gn less or equal to f of n for all n greater equals to n0. We see that this diagram and is elaborate. Next we see theta notation. Theta notation in closed function from above to below is a upper, it have a upper and lower bound and is belonging into middle. Uh, Upper and lower bound is running time on algorithm. It is used for analyzing average case. Is basically used for average case complexity of algorithm. Theta average case, you add running time for each possible input combination and take the average in this case. You can see this graph and elaborate this topic. We basically see that f of n is a function and upper bound is a c dash gn and lower bound is a c dash c1 dash gn. When c2 f of n is belongs to two other to other functions. Mathematical representation, we can see that gn c on gn get lesser equals to f of n lesser equals to c2 gn. We can see this graph and say that this is the mathematical notation. The function f is said to be a omega, said to be a big OG, and there are constants c1 and c2. The natural number of such that c1 gn uh, lesser equals to f of n and c2 gn less c2 gn lesser equals to c2 gn for all n greater equals to n0. We see that this graph. Basically, these are the also two types of asymptotic notation. It's a little o and little omega asymptotic notation. Little o notation is used to be describe an upper bound that is cannot be tight. It other words loose upper bound of an function, let function of n and g of n are the function that map positive real numbers. We can see that is graph is f of n is a function and o of n and omega of n is the little bit upper and lower. This is the elaborate that this is a little o asymptotic notation. Little omega asymptotic notation. Little omega is a rough estimate of the order of the growth where big O omega may represent the exact order of a growth. We use omega notation to denote a lower bound that is not asymptotically tight. Here we can see that this is a little omega notation, the lower bound that is not asymptotically tight and elaborate. And we can see this little o and little omega asymptotic notation. We can see the last slide. Conclusion. Asymptotic notation help in performing analyzing to runtime behavior of an algorithm. Using this, we represent the upper bound or lower bound of runtime in mathematical equation and thus help us perform our tasks with the best efficiency and fewer efforts. Thank you everyone.